Michael is a principal engineer at Bison, Brackin and Associates. I hope I pronounce it well. And he is a specialist in architectural glass design, roadside safety, and physical security barriers. He will also be talking about specialty glass, right? Ceramic enamel coated glass, and what the strength is and how you test it. So, really curious about your presentation. Good luck.
Thank you. Well, it's an honor to be here at GPD this year. I'm looking forward to talking, hopefully, one of the last times about ceramic enamel, at least for uniform pressure. Next time, I hope we're talking about thermal. But what I want to lay out today is a proposed method for predicting the load resistance for a particular type of ceramic enamel. We've done a lot of research in this, and we've had a lot of discussions at ASTM that we'll talk in detail about. You can see my co-authors there. Many of you know Mr. Lingnell and Dr. Beeson. They helped me write this paper. So real quick, a background. So this is going to pertain mainly to ASTM E1300 and how ceramic enamel applies to it. In the United States, for those of you not familiar with E1300, that's how we select the thickness for flat glass subjected to uniform loads. It's a conservative glass selection procedure. If you go way back, the history of it, we started out with what were called the flat line charts, and that was, we originally designed glass based on a whole bunch of testing of different aspect ratios, different sizes, different thicknesses, and all that data was put together, and empirically we would select the thickness of the glass. Then we moved into what were called the squiggly line charts that were first developed by PPG, and that was a result of us being able to calculate stress. The first charts, they were really based on design pressure with a safety factor, and then PPG kind of introduced the stress-based concept where we could actually calculate stress using things like finite difference methods. Computers were coming online, and so that evolved into what is now ASTM E1300. With the development of the glass failure prediction model, now we're calculating the strength of glass based on statistical approaches and the random distribution of flaws across the glass surface. That's particularly important for ceramic frit because you'll see here in a minute, the distribution of flaws across the surface is very uniform. And so that helps us actually predict the strength of ceramic enamel a lot better. What brought this to the forefront, at least concerning ceramic enamel, is we've had a few buildings that have had thermal stress failures. And to date, I'm not aware of any that were uniform pressure load. The ones that have failed, like I said, are thermal stress related, and they're associated with heat strengthened buildings, not fully tempered. So we don't necessarily have an issue with uniform pressure loads and how E1300 applies to that, or an issue for fully tempered ceramic enamel. But what that did was that brought forward the issue of, hey, ceramic enamel is weaker than freshly manufactured clear glass. Does it still apply to E1300, and should we be doing anything about the applicability for uniform pressure? So there was a group that was calling for what they termed a strength reduction factor in E1300, and essentially they wanted to take the design pressure in E1300 for a specific thickness of glass and reduce the strength. And I think the original value was around 40%. The issue with that, and clearly the strength of ceramic enamel is less than freshly coated glass, but that's based on the mean strengths of freshly manufactured glass, not necessarily in-service strengths. So the problem with applying that directly to E1300 is E1300 takes into account what some people term the weathering process, or just the in-service issue of all these flaws getting distributed across the glass and changing the strength. So a good number, ballpark number, is E1300 is operating on a 50% reduction in strength compared to freshly manufactured glass. So there's really no clear evidence to say we need to reduce the strength for ceramic enamel as far as E1300 and uniform pressure loads go, but we had to do some research and testing to show that. What has developed is there's going to be a note added in the next revision, and it's going to essentially state that ceramic enamel is known to affect the strength of glass, and you should contact your manufacturer to figure out what that means. Now, the question is, what does the manufacturer do with this information if somebody calls them and asks? And so that's what we're kind of laying out here today. So the best way, like I said, to figure out does ceramic enamel negatively, or does it meet E1300 or not, the best way to tell that is to test glass, right? So what we did was we actually tested full-scale plates. We compared that to E1300 just to figure out where we're at in the process here. We tested 40 by 60 quarter-inch specimens. I'm from Texas. I like inches and feet, so you have the millimeter dimensions up there. Old habits die hard. But we tested we tested a lot, but this is the example I have for you here today. 10 uncoated clear glass plates, freshly manufactured. They were heat strengthened. And then we tested 10 enameled glass plates that had a light gray coating. They were roll coat applied, 4 to 5 mils of wet thickness. They were full flood. We did test some patterns and things like that. Patterns, the thickness of the coating, obviously heat strengthened versus temper, all that plays into the strength of the glass and how the frit behaves. The glass was sent to us by Glass Coating and Concepts. They were the coating applier. Who fabricated the glass, we weren't aware of, but we tested that in our lab in College Station. So I had to throw this picture in here. That's at Beeson Brackin, we believe in nepotism. That's my son when he was 3 or 4. So this testing was quite a while ago. He actually just had his birthday last month and he turned 10. So it's been a while since this was done. One of the interesting things that we learned in testing ceramic enamel, I mentioned that the flaws are very uniformly distributed across the glass plate. What that means is that we can apply a maximum stress model to calculating the strength. So I've got the fracture origin circled down here in this picture, and if you've done an analysis on plates, you know that this is one of the zones where you get a lot of high stress. And so almost all of the plates, I can't think of an example where it didn't break in a zone that wasn't high stress, the highest stress on the plate. So comparing the loads, uncoated glass, we've got a mean 3-second breakage load of 500 PSF. For the ceramic enamel, that drops down to 288. But what's significant here is the coefficient of variation. You can see that we dropped down from 8% to 3%. And so, again, that's that uniform distribution of flaws across the glass plate. However, we're still 2.4 times the design strength of ASTM E1300. So the problem with testing full plates, obviously, that's tough. They're heavy. You got to build the test frame. That's expensive. Transporting big plates is expensive. Making big plates is expensive, and it's not necessary. So what we've figured out is that you can actually test simple glass beams, 4-point bending, and you get the same results. They are a little conservative, but both methods, plates and beams, show about a 40% reduction in the strength. If I remember the numbers correctly, the plates were roughly 43% strength reduction. Oh, no, the beams were 43%. The plates were roughly a 38% reduction, so right around that 40% mark. So what I'm going to lay out today is basically a real simple design procedure that you can take and apply to different types of ceramic enamel coated glass, test it, and get your strengths. We're going to use 4-point bending test, your common load corrections for static fatigue. We're going to apply our normal statistical distribution that we do, same thing for E1300. And then we're going to look at the design pressure in E1300 and take the smaller of the two. So real quick, I'll go through the steps and then we'll talk about these each in detail. obviously, whatever you're testing, you've got to have a representative sample. We typically like to test 30 specimens, 20 to 30 at least. Step 2, you've got to have a real good measure of your residual surface compression for those specimens. We're going to 4-point test them. We're going to calculate, now this is kind of the new step here. We're going to calculate the net breakage stress. So this will be your net tensile stress in the beams. We're going to adjust that data for static fatigue. We're going to apply our statistics, calculate mean, standard deviation, and then from that, step 7, we're going to get our 8 per 1,000 design, probability of breakage design stress. Now, well, step 8, what we're going to do is we're going to take that net tensile stress, design stress, we're going to add back our residual surface compression, and it'll give us our total design stress. From there, everything is your normal design process. You're going to figure out what is your stress in your glass plate. So that'll be your typical geometric nonlinear analysis, run a finite element model, however you get those stresses. And then take your design stress and figure out what load you can apply to that glass plate. And then we'll look at E1300, figure out the design load from that, and then we're going to take the less of the two. So we don't ever want to design greater than ASTM E1300 or the strength of the ceramic enamel. So for this presentation, I've got